So let's do it. Yeah. So let's finish up these slides about social media et al. So the last thing that I want to talk about for these slides are just technology in general. Evaluating and controlling technology. Let me pull up my notes real quick. Interesting. Yeah, so this is the kind of question I'm going to try and answer. Technology, it's great, right? We love it. We're using it right now to sign into class even, but it has some definite downsides, as we have discussed and as I'm sure you know. So how can I cope with them? How can I live with technology still? Maybe we should just get rid of it all. And how can we think critically about it still? Okay? So yeah, let's talk about some downsides and what's going on there. So have we heard of deepfake before? That's kind of old news, right? But that is when you use machine learning, that fancy tool that's all the rage these days, to take a video. You have like a feed, a video feed, or a video that you've already recorded, and you can swap a face out with somebody else's in the video itself. Isn't that cool? So when this first came out, everybody wanted to change everyone's face to Nicolas Cage for some reason, and so these are those examples. But that's weird, right? You can change somebody's face in a video, and it will look like somebody else. It's like they were really there, but they weren't. So that's weird. We could already do that with Photoshop on images, right? It was very easy to always be able to swap somebody's face out with somebody else and make a doctored photo that makes it seem like somebody was in a place, but they really weren't, with a still photo. But that wasn't a very normal thing to do. It was very hard to do for videos. All right? So we used to be able to rely on videos, right? Like for security cameras and stuff like that. A video of somebody doing something used to be pretty good proof that they were actually there and they did that thing. But no more, now that we have deepfake, right? You couldn't trust images because of Photoshop, and now you can't trust videos because of deepfake. So, yeah, this has been already used for fraud, make it sound like somebody's talking to you when they really aren't. Hoaxes, of course, pretend like somebody's saying something, but it's not really them. And all of the memes that can come with this as well. So, yeah, that is deepfake. And we have to kind of reassess what it means to be credible now, like a credible source of information, now that we have these things. Okay? Which is no fun, but that's just the world we live in. So that's the first one. Please shout out if you have any comments or questions about this stuff. It's fun to talk about. So, next thing, let's talk about Wikipedia, okay? Because I'm sure we all use Wikipedia. It's a very, very useful resource, but Wikipedia is, of course, a resource that is open to anybody to change, right? People are adding / updating articles on Wikipedia every single day, okay? So the information yesterday, like here's your article, it might have been this long, and then something new happens, and then people come along and they add more stuff. Like there's new information the next day, which is great because you're getting the most up-to-date news information all the time. Wikipedia is the ultimate news article, you could say. But the downside to that, of course, is that anybody can modify Wikipedia. And so I'm sure this is why you've had English teachers in the past saying, don't cite Wikipedia, don't cite Wikipedia. This is the reason. Anybody, no, doesn't have to be a credible source, could modify a Wikipedia article and say whatever you want. You could edit an article and put weird / incorrect information. Like I could go to the Clovis Community College Wikipedia page, and instead of the logo, I can put my cat's picture or something, right? I could make it incorrect, and it's some other human's job to come around and say, oh, yeah, that was probably not correct, not fake, or not true, okay? There are ways to automatically discover that a Wikipedia article has been doctored, but there's also just an army of humans looking at every change to Wikipedia It's crazy though, okay? Sometimes it takes a human a little while to come along and remove that inaccurate information from Wikipedia. So there's always that button, right? I don't know. And wikipedia.org, what's the article of the day, whoever this person is? It's a book. You can go to, honestly, because it's the article of the day, you might not get to edit it, but maybe you have to log in. I don't know. Let's go to main. There it is. There's the edit button. So you can click that and you can change the article, right? You don't even have to be logged in. That's no fun. You can make fun of Maine if you wanted to. So that makes it hard. That's why English teachers don't want you to cite Wikipedia. They want you to cite the citations, and I would prefer it if you did that too. Cite the citations, because those are the credible sources down here, right? All these guys. And that's why maybe you've seen a bunch of articles that say citation needed all over the place, because they're just spewing words out without backing them up, right? So that's the downside of Wikipedia. Does that mean you shouldn't use it? Of course, would be the next logical question. But I think the answer would be no, right? You could totally use it as long as you do your own research based on Wikipedia's research, right? Go and actually visit those articles that are being cited, right? And then that's where the source of the information lies. Confirm that it's a credible source, and then use that in your essay, okay? So that's my opinion on Wikipedia. I don't know if your English teachers are a bit more strict about it, but that is the idea. Any questions about that? Has anybody seen a Wikipedia page wrong before? Been vandalized? That's true. It might be obviously wrong, or it might be just subtly wrong. That's a very good point. I was on Reddit the other, last semester or something, and for some reason it linked. There was a link to the California grizzly bear. I have no clue why, but somebody had modified that page in the time that I got to look at it, and you can vandalize Wikipedia pretty easily. Just press the edit button, okay? And so that's a very common thing that happens. It is, this happened to me. I noticed that. And then, of course, there's automatic change detectors. Probably a minute later, if I had visited this article 1 minute later, it would have gotten reverted back to the original article, the correct one. But yeah, that goes to show that the information that you see on Wikipedia is constantly changing, and it doesn't have to be correct. Crazy. All right.
Should that make us more cautious? Can people embedding sites and links in Wikipedia?
I would say so. Yeah, don't just trust okay, this was citation 25. Okay, this sentence is backed up by citations 25 and 26. Just the fact that there's a link here doesn't mean that the article was credible. I think you should go to it, make sure oh yeah, the National Post, maybe I've heard of them. I'll trust that. Rather than somebody's website, somebody's blog, something like that. That's a good point. Boop. So yeah, Wikipedia is a fun can of worms. Let's keep on trucking with, oh gosh, did I go a little too far ahead? Yeah. Okay, so let's next talk about car crashes. This is an interesting concept. So we have made some very fancy programs that can simulate what it would be like for a car to crash. Okay? So you have to do those crash tests when you develop a car, right? You got a little wall. Maybe you've seen these commercials back in the day. Got a little wall, and you have a car drive into that wall, hopefully, and it doesn't harm the little dummy man inside of it, right? Here's your car, boop boop, wheel, car, and they have a little crash test dummy inside of it, and they're sending that in to the wall, and that's how you test whether or not the car is up to the safety standards of whatever country it's being developed in. It costs a lot of money to run this experiment, right? Because it costs you a car, yeah? You don't get the car back after you crash it into the wall. It's kind of totaled at that point. So wouldn't it be nice if you could simulate the car crash with a fancy enough program to see what would have happened had you really crashed that car into a wall in real life. So turn all this, just put it inside of a computer so you can run it a million times on your laptop. Wouldn't that be cool? That's what people are doing these days. And so you can test your layout for the car, the design for the car, virtually, and maybe change it a little bit based on those virtual results so that you know it's going to be good when you do it for real. Okay? So that is something that exists these days. You can simulate car crashes in software, and you have to model like all the physics and stuff. So yeah, how do you implement this program? How would you write this program in Python or something? You would have to model every little detail, right, of every little material that is in the car. You have to model the exact type of metal, the whatever alloy it is, how it crumples, how it reacts under stress and heat. You have to model where every indent for all the screws and the frame are, stuff like that. You have to go down to that level. You have to model the car at that level. You essentially have to play God. You have to model every bit about physics down to the atomic level if you can, right? That's not really possible, though, inside of a computer. You cannot model each atom of the car's structure. That would take way too much computational power that doesn't exist in the universe, right? That's no fun. So you can't have a perfectly accurate solution here. You can't have a perfectly accurate simulation inside of a computer. You're going to lose some information. Does that make sense? You can't model real life perfectly inside of a computer. So you have to simplify stuff. You have to make simplifications. You just consider, like, okay, we're going to consider square centimeters of material at a time, nothing smaller than that, and see how they all hook up together and interact. Something like that. So you have to make those simplifications, and so your simulation is not the same as what would have happened had you crashed the real car into a real wall. The results are not exactly the same. But maybe they're close. The question is this okay? And the answer is probably, is the result close enough for some definition of close enough? Okay? There's plenty of arguments in either direction here. Like, should we be using these simulations at all? So one argument for simulating car crashes in software is that, yeah, eventually they're going to like simulate it enough times, change it a little bit each time, make a good performing car in the simulation, and then they'll build the car, right? Then they'll build it, and they're required by law to actually perform a real crash test on that car. Maybe the car would have been safer. Like, they get to do more iterations on its design because they don't have to keep building it. They get to save money by just simulating the crashing. So maybe it'll be safer in the long run because you get to improve it more than you would be able to otherwise. So that's one argument for the car crashes being simulated. But the counter argument is, well, that simulation is imperfect, right? Maybe they would have made a final safer design if they just spent more money and did more real car crash tests and updated their cars based on the results of the real tests. What's really happening in real life. Okay? So, arguments for and against, you can go either way. I think most car companies are trying to save money, so they're going to do at least a few simulations these days. But that is the state of them. Questions, comments about that? It's fun to think about. Let us move on, assuming I don't accidentally change things. There we go. Next thing, Google. I think Apple can do this too, but if you have like an Android phone, Google can delete an app that you have downloaded already from your phone without you interacting with it, saying yes or no. Google has that power because they make the Android operating system, right? They have the power to remove stuff from your phone. They can get rid of that app if they want to. And the reason why they have this power and they give it to themselves is so that they can like protect your grandparents who have Android phones and accidentally download something bad that was somehow allowed to be on the Google store, but they realize that it was bad and they take it off, and then they get it off of everyone's phone who downloaded it. Something like that. That's the reason why they do it. It's supposed to protect against bad actors, malicious applications, let's say. But there is kind of a slippery slope there, I think you can imagine. Should they be allowed to do this at all, is the question. Because maybe they'll, like, if they have this power, they can abuse it. They can remove an app that kind of competes with Google's normal apps, something like that. Should they be allowed to do this at all, is the question. Who knows? There's definitely arguments and counter-arguments, for sure. Apple is also allowed to do this. They have that power too. They've also taken things down. I wouldn't say recently anymore, but do you remember the uproar, like maybe a year ago, about Fortnite on iOS? Apple took Fortnite off of the App Store because they broke the App Store rules. And they were protesting against them. Apple wanted 30% of all money that's made inside of apps. Every in-app purchase, they say, anything that you buy inside of an app is called an in-app purchase. And Apple takes a cut of that money. They're supposed to. Fortnite didn't want that. And Apple's been given deals to people like Netflix to not have to do that. So they thought it was unfair, and they didn't give Apple the cut. And that got them removed from the App Store, and that caused a lot of drama, if you remember that. So, yeah, is that okay? They were disobeying the rules. There are rules to be on the App Store, and they didn't follow them. But does that mean, is that fair, I guess is the question. Apple is allowed to remove those things from the store. If you downloaded it already, you got to keep it. But they weren't letting other people, new people, download Fortnite back then. I'm not actually sure what came of that. I didn't research it after the fact. Maybe it's still not on the App Store. We should search that, figure it out. But yeah, that's something that a company can do. If they provide an App Store, they can take away apps. That's for sure. Okay? And then a very fun example, excellent irony, is Amazon, who sells Kindles, of course, where you can buy virtual books. They accidentally removed copies of 1984 from everybody's Kindle who downloaded that particular copy of the book, which is extra hilarious if you have read 1984. All right. Yeah, so that's kind of scary. We don't like that. Or maybe it's a good idea for at least our grandparents or our parents who are getting old. We don't trust them with technology. It would be nice for Google to get rid of bad programs for them. Let's next talk about forced upgrades. If we have technology, again, it's owned by somebody, like Windows is owned by Microsoft. They like to change Windows and release new versions of it. Some people have been forced to upgrade to a version that they didn't really want to upgrade to. So Windows 10, for example, keeps yelling at you, like it kept yelling at me, please update to Windows 11. Your computer is able to update to Windows 11. Why don't you do it? And I still haven't done it. But this was a thing, especially back in maybe, I think it was Windows 7. There was like an automatic update to upgrade to Windows 8, and everybody hated Windows 8. Kind of like people don't fully enjoy Windows 11 as much as they liked Windows 10, I guess. But yeah, if you don't pay attention, you can be caught in an automatic forced upgrade. You just don't press no enough or something. So then there's a question about autonomy, right? Do you actually have control over what's going on your computer? Do you have control over what exists on your computer? Because if the operating system is owned by Microsoft or owned by Apple, they can kind of update things automatically for you, maybe without you having configured that. That might not be a good thing. And so again, there's arguments for and arguments against. An argument for forcing an upgrade to happen is that, one of the reasons for upgrades is that there are bugs. There are bugs that are being fixed, and some of those bugs in the software are exploitable. You can hack somebody's outdated version of Windows a whole lot easier than you can hack the most recently upgraded version of Windows, right? So it would be really nice to just have automatic upgrades happen for you, because then it's harder to exploit that software that is on your computer, right? So That's a good argument for, I would say. But an argument against is just autonomy again, right? So the second somebody is forcing something upon you, you don't have control over what you bought anymore, right? You bought this computer. You don't have control over the software that you installed, maybe, if you built your own PC or something, or that was installed for you when you bought your computer. That's silly. You expected to have some amount of control and you lost it. So again, there's always two sides to this, but I want to show you the problem and have you think about it. All right. Let's see, how do I want to do this? So yeah, last slide for these slides. We're like in between lecture slides today. We'll do a little bit, we'll finish this one and do a little bit of the next one. But the last main topic is about equity. I hope we've heard that term by now and we know what it means. But equity with respect to technology is a very important and interesting problem, I think. So, especially after the pandemic, right? Because think about it. Think about someone from a low-income household and think about whether or not they have a fancy computer, whether they have an internet connection. It's kind of required these days, isn't it? There's a lot of help that you can get, but maybe not enough. A lot of low-income households do not have the things that they need to improve their lives. You need an email address these days to, like, apply for a job even, don't you? If you don't have a phone or an email address, you can't even get an interview, something like that. So that's a problem. That is a huge problem these days with equity. And during the pandemic, it got worse, right? Let's pretend that we're still in the pandemic, maybe. So, for example, everybody was at home working or going to school, and maybe you were taking like a class that was easy to cheat in, and so the professor required you to like use Proctorio or whatever that thing was called, and you didn't have a webcam. Then you can't use that service, right? They can't proctor your test virtually anymore, and you can't take that particular class, can you? So that's a huge, huge problem. So maybe we should have been giving more people webcams, and we were doing that here at this college. At least we were doing it well, but I can assume that some schools weren't handling that very nicely. So yeah, an extra bad problem. Oh, actually, do we all understand equality versus equity, by the way? Like, this is the standard picture that everybody shows. Equality is, let's give everybody this nice thing that can help them, but some people need a little bit more, right, than others. This is equity over here. Some people need $2. Some people need $1. Some people don't need $1. They're good already. That's what equity means. So yeah, think about that with respect to technology. We're checking out things to students who need them at this school, for example, like laptops, webcams. Yeah, final problem. Again, came up in the pandemic. I have a fun tweet on the next slide. But a lot of the time, programs are tested only on the people who work for the software company, and the people who work for a software company are predominantly white. So they're testing the programs on themselves, and if it's like a machine learning program, it's not maybe going to work for somebody with a different skin color, which is unfortunate, right? So even if somebody gets the fancy technology and they have the money for it, it might not even work for them. And so here's a fun tweet to close that out. This person was using some sort of proctoring software, but it couldn't recognize them. So that there was poor lighting in the room. But no, it's just because they tested the program on white people. That's really unfortunate. So that's the kind of thing that comes up. And so I hope when you make your fancy software startups one day, you consider this problem. Okay? And that is all I have to say about this. Any questions, comments about these slides before I switch to a new one? All right, so let's talk about problems. And so I've had you read a little bit about a certain kind of problem. Hopefully you've started on that. because we're going to talk about that one today, among others. So lots of fun issues to talk about. Computer risks and bugs. Let's start with errors, failures, and risks. Okay. There are issues with using a computer. Programs crash. Things don't work the way they should. There are bugs. Should we just throw away computers then? The answer is probably no. But how in the world can we keep using computers when they cause so many problems, and some of those problems are big problems? Let's talk about some big problems that have come from computers. The first one is a rocket called Ariane 5. Okay? It was a rocket made by not NASA, but let me zoom in here. ESA, European Space Agency. ESA, I don't know how you pronounce it, but ESA, it's the Europeans having a space agency, and they were trying to launch this rocket, Ariane 5, assuming, there had been an Ariane 4, Ariane 3, Ariane 2, Ariane 1. They were doing pretty well, but this particular rocket did not do very well, okay? It self-destructed, which was like a fail-safe mechanism, back in 96, after only flying for 37 seconds. 37 seconds after liftoff, it blew itself up because it thought that a horrible, horrible problem had happened when it really didn't. It was doing just fine, but it was a software bug that told this thing to self-destruct. Something is super, super wrong. We better abort the mission and blow up. Okay? So this rocket cost $370 million to make and develop, and they lost it all after 37 seconds because of a couple lines of code. So let's talk about what went wrong there, because I can actually explain exactly what went wrong to you. You know everything now. No, luckily this was just an unmanned mission. It's just a rocket test. I think it was one of those automatic ones that launch satellites or something. So luckily nobody was on board. It's not that one of those extra sad ones. It was just a lot of money lost. Better than the alternative, for sure. So here's the problem with the Ariane 5 rocket. What they did was they tried to shove a 64-bit number, a 64-bit float, right? Remember what that is in Python? A float, remember that cloud? That was my numbers with decimals in them, float. That could store 3.14. That could store 5 times 10 to the 10. Large numbers, small numbers with decimal places, stuff like that. That's what floating point numbers, that's the fancy term, can hold. That's what the float type holds. So that number was made of 64 bits, so it's just 64 ones and zeros, right? 64 binary digits. So they had that number, that was a reading. They took that, 64 binary digits, and they tried to shove that into a 16-bit int. Remember what an int is? Those only store whole numbers, right? Maybe they rounded it, that was good enough. It's 42, 0, 42, all that stuff. It's not a huge problem in itself. You chop off decimal places when you convert like that, but there was a bigger problem. So they tried to take all this information and shove it down into 16 bits, 16 ones and zeros, and I think you can imagine that's a quarter of the space that has the potential to be an issue. Okay, so that's what they did. That's what all those words mean together. So they tried to take a 64-bit float, so a 64-bit number with decimals, and shove it into a 16-bit int. So an int with only a quarter of the space, so you can't hold as many numbers as a float could have held. Okay? So the number that caused the bug was the horizontal velocity of the rocket. That was a reading that the rocket was taking of it for itself. And here's what my best guess of the horizontal velocity means. Here is the rocket, or here is Earth, and here is Europe. There's Italy and all that. Here's the UK. Boop. So the rocket was taken off. Boop, boop. heading off of Earth. There's the rocket stream. And I think that horizontal velocity is always relative to Earth. So it was shooting off at an angle, and it was like moving a little bit this way relative to Earth. It was also going up, of course. I think that's what horizontal velocity means. And that number that it was keeping track of, it had like a GPS on it, keeping track of how fast it was moving relative to Earth, what direction relative to Earth. The number that it was taking was stored in a 64-bit float. They shoved it into a 16-bit int, and it overflowed, is the word. An overflow means that you didn't have enough space to store the number that you needed. So, for example, if I only have 4 bits in a number, let's pretend we only have 4-bit numbers. Like this is the smallest 4-bit number, and then the largest 4-bit number is 1111 base 2. If you tried to add one more number to 1111, let me do binary arithmetic for you right now. Here's what happens. 1 plus 1 is 1, 0 in binary, 1, 0. You carry 1 plus 1 is 1, 0, 1 plus 1 is 1, 0, 1 plus 1 is 1, 0, 1 plus 1 is 1, 0. You only have 4 bits to work with. This largest binary number became 0. That's what an overflow means. We didn't have any room for a 5th bit. We were only working with 4-bit numbers for this little green example. We had no place to put this carried value. The answer was really supposed to be 1, 0, 0, 0, 0, but we don't have room for that one. So it kind of goes off into the ether. And that is unfortunate. So this is the kind of thing that happened. They had a very large number that could not have been represented in 16 bits, and they tried to put it in 16 bits, and they couldn't. It wouldn't fit. Okay? So that's the whole problem. That's what they did. Okay? And that was what caused it to self-destruct. It's like, oh gosh, my horizontal velocity is not at all what it should be. It's way too small. That must mean that I've lost thrust or something. I better blow up before I crash into something. So that's what happened. And the funny thing is, this code that caused the bug in Ariane 5 worked before. They used the same code in Ariane 4. They just copied and pasted it, essentially. And what used to work, shoving these numbers like this, it used to work for the Ariane 4, but it had a less powerful rocket on it, I guess. So they reused the code from the Ariane 4, and back then they thought that the horizontal velocity number wouldn't ever get so large to overflow a 16-bit integer. Oh man. But no, the Ariane 5 went a bit faster, and so that caused the bug. It was not apparent. They thought that the code was perfect. It worked just fine for the old model of the rocket, but it didn't work for this one. Okay, so that, honestly, just a couple lines of code probably to fix it, that caused the issue. And it cost them a lot of money and a lot of credibility as well, right? Because once something like that blows up, I'm sure you have a lot of investors. They're not going to be as quick to give you money again if your rockets blow up. So, yeah, that was the Ariane 5 issue. Just a software bug. Very, very expensive software bug. Any questions, comments about that one? What's that? Yeah, 96. So relatively a long time ago. They've gotten better for sure, but that was a sad day for them. All right, let's keep on trucking then. Next issue that you can have is a place that you probably don't want to have an issue. Voting systems. So these are some fun anecdotes from the book. Back in the day, there used to be, I know California doesn't do it, probably for this reason, but some states probably still do, right? That they have electronic voting systems. So you go to the polls, you press a button, you don't write anything on paper. And it's a computer that's counting the votes. It's not a human. So there are some potentials for bugs there, and there have been bugs. So here are some examples. Some electronic voting systems crashed on an election day. That caused a bunch of voters who wanted to vote to become unable to vote, right? Maybe they took down their votes on paper, but who knows if those were counted. so it was kind of like extra. So that's a horrible problem. You need electricity to have an electronic voting system. If the power is out, if there's a hurricane and it's election season, you can't vote suddenly. That's unfortunate. So that's one problem. One county lost about 4,000 votes, which is relatively not too many, but maybe it was a local election. They lost like 4,000 votes because the memory of the voting machine was full. It couldn't hold any more votes. Too many people had voted for it. That's kind of like an overflow problem, kind of. That's unfortunate. That would have never happened with paper. You just make more paper. In one county, a programming error generated 100,000 extra votes for somebody. Luckily, they caught it because it was just for one county. Like there aren't that many people registered to vote in that county, so they noticed it. But still, you can think about this. If the error wasn't as apparent, it would generate like, I don't know, 10,000 extra votes for somebody. Maybe that will go unnoticed, and that will cause them to win the election. So that's a very unfortunate thing as well. And then finally, probably the worst kind of error is this last bug. A programming error, a bug in a voting system, electronic voting system, made it so that you pressed the button to vote for one candidate, but that actually gave a different candidate your vote. So it wasn't hooked up to the right person, which is probably the most horrible of all the options. Okay, so yeah, these are times that you really want correct software and you're not getting it. These are issues with voting systems. So the moral of this story, I guess, is that it's really hard, all of these examples, it's hard to write correct software. You've been writing code in this class. I'm sure you understand it by now. It's hard to get it right the first time. And there are bugs that can just persist without you noticing them for a while. It's hard to write software that's correct, that's safe, that can't be messed with. You have to assume the worst, I guess. And there will always be issues. There's always updates because there's always problems, right? So that is one reason why California uses paper votes and humans counting them. So yeah, this is not to say that this is an unsolvable problem. Estonia, for example, every Estonian citizen, they vote online for their highest level of elections, even. And they have no issue with it. It's worked just fine for them. So if you test it enough, it'll eventually work out. But along the way, you're going to have these kinds of problems that will have people lose trust in the system. Okay? Any questions about that? All right. Well, let's keep on trucking then. A couple more slides. So let's get to the topic of your essay, right? Let's talk about the Therac 25 and the horrible, horrible issue with that one. This one caused human problems, right? Problems with actual people and their health. So the Therac 25, it was a radiation therapy machine. So if you had cancer, back in the day, this was like the latest and greatest machine that you would be taken into a room and this would be shot at your cancer, right? The Therac 25 would be programmed, okay, this is where the cancerous cells are, please shoot some radiation there to hopefully kill them. Okay? And so this was first made in 1982, that's when it first came out, and the first accident that was documented, I think once we get through this, or if you've read it already, you can imagine that plenty of other littler accidents had probably been taking place since it first came out. The first documented accident with it, though, came out in 1985. Okay? So this is a while ago, but it was a huge, huge problem, a horrible, horrible disaster. So there were bugs. This was a software system, right? It was software that was controlling some very important hardware. There were errors in the design of the system as well as errors in the code itself that ended up giving people who were supposed to get a certain amount of radiation, they were given up to 100 times the amount of radiation that they were supposed to get for their cancer treatment. And so that's the ultimate and the saddest form of the issue that you can have, because somebody who was expecting to have their cancer go away suddenly got more cancer, right? because radiation can cause that, of course. So people lost lives because of this problem, and it's important to talk about. So yeah, here was essentially the issue. You'll read about this more if you haven't already for your essay. But again, they did the same thing that they did with the Ariane 5. They took code from a previous system that had worked, but it didn't work in the new system because some things had changed. Some assumptions have changed. Some things are new. Okay? So let me make my best drawing of a radiation beam. Here's kind of what was going on. Here's like a little, let's pretend this is a source of radiation. Here's a little cylinder, and it's going to shoot out radiation at somebody's cancer. Previous versions of the Therac machine, like the Therac 24 or whatever it was, they had a hardware system in place. So like when the system wasn't on, they were kind of like hooking it up and trying to coordinate where it should go. There was like a lead ball right here or something, a lead plane of metal or something. There was a piece of metal there that was blocking this radiation beam from shooting anything out. It was blocking any excess radiation while they were hooking it up, stuff like that, while it was being programmed. So that was keeping any excess radiation from coming out in the older versions of the machine. Okay? And the issue is they thought that the software was good enough. Like, oh, okay, nobody's getting any excess radiation. We don't have to include this little lead beam anymore. We have to include this lead. What's the right word for that, even? I don't know. We don't have to include this piece of metal to stop the radiation because it's working so well. We found nobody getting excess radiation, so let's just get rid of this. So they got rid of that, and there was a bug in the software that was sending excess radiation out, but they didn't notice that before. That was the problem. And now that they didn't have the fail-safe of this lead sheet, suddenly the radiation could get out, and it was harmful. Okay, so that's the Therac 25. Any questions about that? Comments about that? It's a very sad thing to talk about, but it's very important to learn, especially for those of you who are going to go into a software job, software career, or hardware career. So that's the Therac 25 machine. People were hurt and killed because of a software bug. All right? So now I have a question for you. So let's get together in our peer instruction groups, and let's go to the written ice page, let's say. And I have a little mini debate for us. And that'll be most of what we're going to do today. So please get together. Sorry to give you a horrible topic to talk about, but here's our debate. I'd like you to think about this. Is it the programmer's fault when something bad happens and people get hurt? Because this Therac 25 machine, was programmed by humans, maybe a large group of them. Can you point the finger and blame one person or the whole company or what? Is it the programmer's fault when something bad happens and people get hurt by your software? Okay, so instead of being like even and odd, because we know we're all even these days, let's just come up with one argument for each side. So every group come up with a good argument for yes, it is the programmer's fault, and come up with a good argument for no, it's not the programmer's fault, and give some backup as to why. Okay, so I'll give you a few minutes to think about that and discuss, and then we'll come back. All right, that's my timer. Let's see what we were thinking. Let's come back. Is it the programmer's fault? Like, if there are probably logs, like there's whoever caused this radiation to accidentally come out, there's probably a line number for the code where that was the problem, and you can point to a single programmer where that was written, or maybe it was a bunch of people who were touching that code because it was made by a big company, something like that. Let's see what we were thinking. Did we think of all those ideas? So yeah, here's a yes answer. It's the programmer's fault. They are responsible for monitoring their own written code and recognizing issues of faulty backwards compatibility. Yeah, you'd think that would be easy to do, but is apparently not. Yeah. So it's the programmer's fault because they were negligent. They didn't check for mistakes. And it's not the programmer's fault because there should be other people. Maybe there should be somebody whose job is solely there to make sure that the program's going to work. Just some testers. That's technically a job. Like there's, you can be a software tester rather than a software engineer. That's a very, very important job to have. So yeah, I'm glad that we were thinking in both ways. So no, you can't really predict. No human has the brain power to predict exactly what's going to happen inside of a program. It's infinite possibilities, right? A lot of the time. That's a great argument. And then for yes, engineer, programmer should be held responsible as human lives were extinguished even if by accident. So yeah, there needs to be a blame on somebody, right? So these are conflicting ideas, but they're good because I want you to think about both. If the programmer knows it can harm, ensure their programming is proper. Yeah, try as hard as possible to make sure that you can't cause any harm. But maybe they don't know. That's the flip side, right? The company is at fault. Yeah, maybe they should be paying someone else to check their code for them. So yeah, these are good ideas. I like it. So it's hard. It is really hard to point a finger to attach blame. Because that's the question. How do you assign blame to this? Right? Usually, a lot of the time, and I'm sure it was the case for the Therac machines, there were a ton of engineers working on the hardware and a ton of programmers working on the software. And a lot of people, like there was a huge team of them, right? And some people were working on maybe just small portions of the software that, like, they knew that small portion was correct, that the stuff that they wrote was correct, but maybe they weren't really, it wasn't clear to them how their part would play, or how their piece of code would play nicely with other people's pieces of code, right? That's hard to figure out, especially if they're just over here writing their own little piece, right? It's hard to see the big picture, and that makes it easy for bugs to come through, okay? And by now you definitely know that it's hard to write a correct program. I'm sure it's taken you a few tries for some of these last few programming assignments, right? You can't get it right the first time, and it's very easy to make a program that does something wrong just subtly, right? And it takes some debugging. Just imagine for a piece of software as big as a cancer radiation machine. It's even worse, okay? So the real way that you would have to go and solve this problem, the solution that should have been there, was more testing, more verification, making sure that the code was correct, right? Weirdly enough, the word testing and the word verification, though in like a dictionary they do mean the same thing, they do not mean the same thing in computer science. So I'll tell you the difference. Let's see here. Yep, I think that's what I wanted to say. So, let's talk about testing. I'll talk about verification next time. Testing is when you come up with an idea of what your program should do, and then you make sure that thing actually happens. So you can make a bunch of tests in that way. Compare what you expected to what you got. So, testing is a very easy way to catch bugs, but it's not going to catch every bug because you as a human have to make a bunch of tests, right? Maybe you made perfect tests, but a lot of the time your program could have infinite possibilities, and you can't have infinite tests, okay? A lot of the time, though, people hate writing tests, which is quite sad. That's one thing I like to do in my major CSCI classes. I force my students to write a bunch of tests. So here's essentially what a test should be. Your code, you treat it like a black box, because it kind of is. Like, you think you understand it, but maybe you don't. So here's your code, and here's what a test does. It runs your code with a certain value. Like maybe your code takes some input that's a number, and it spits out an answer. Like maybe if you give it 42, the output is 13. A test is saying, all right, if I were to enter 42, my output should have been 13. So let's actually run our code on 42 and make sure that the output was 13 after all. Okay? So that's like a passing test. And then maybe if we run our code on, 43, we should get 14 back. But we ended up getting 88 back or something like that. And so that was a failing test. So you always come up with an idea of what your code should have done, and then you see if that really happened. Okay? So that's what a test is in computer science. So here's an example test just spelled out. Example test. So try input 42. Confirm that the output of your code makes 13 as the result. That's all a test is. You have to come up with good ones, though, and a bunch of them. Confirm that the output is 13. Okay, so does that make sense? That's what a test is in computer science. You have an idea of what your code should do. You kind of like run it in your mind, and then you make sure that your code actually gave back that answer that you thought it should. Okay. And so I think I lied, actually, when I said I wasn't going to program today, because I have one slide about programming. But let's write a single program and a test. Let's do it in Scratch, though, because we know more Scratch. I can't really do it very well in Python right now. So let's make a block. We know how to do that in Scratch now. Let's make a multiply the numbers from 1 to n block, and like you can put anything here. That's your input. Like multiply the numbers from 1 to 4, and that should give back, 1 times 2 times 3 times 4, which is 12, 24. So like if you input 4, the output should be 24. That's 1 times 2 times 3 times 4. Multiply all the numbers from 1 to 4. And so that's a test. That could be a test. Multiply all the numbers from 1 to 1. That should just be 1 by itself, right? The result should have been 1. That's a test. Multiply all the numbers from 1 to 2. Give 2 as the input. That should be 1 times 2. The output should also be 2, right? So those are a bunch of tests. And if we get all these passing, we can be pretty confident that our code is correct, right? That's what it means to write tests. So let's make that block. Let's write some tests, and let's compare that we got what we expected. All right, so let's go to Scratch one last time. Why not? Scratch.mit.edu. Go away from the main Wikipedia article. And while that's loading, let me just make sure. Okay, yeah, that's all I want to do today. So hello, Scratch Cat. One more time we get to hang out with you. Or I guess I just want to make the block. Let's go to My Blocks. Okay. And it's going to take one input, and we'll call it n, I guess. And it's going to be multiply the numbers from 1 to 2. That's the name of the block. Takes an input, though. Okay. Multiply the numbers from 1 to n. And now n is the variable that's going to be used. So like if I use this down here, multiply all the numbers from 1 to 4, for example, it should give back, or at least print, the answer, right? I guess, yeah, we're kind of forced to print the answer for this one. So can't really give back a value very easily in a Scratch program from this. So that's all right. Actually, can I make like a different kind of block? Darn. Okay, no. I was getting excited. So yeah, let's see what happens when we run this program. Let me just quickly do it. It's very similar to the sum program that we've written before. We just keep, like we have a variable n. That's going to be set to 4 or something. And then we'll keep an accumulator variable. We'll call it like product. And then, let's see here. That'll start at 1, because we want to multiply stuff into it. Can't start at 0, because then it'll just stay 0. So let's start at 1. And we'll repeatedly multiply our n into products, like multiply 4 into product to make it 4. Then subtract 1 from n to make it 3, and then we'll put the 3, multiply the 3 into product. That becomes what it was, 4 times the 3, so that makes it 12. And then subtract 1 from n. That's how we can do this. And then multiply the 2 into product. It was 12, multiply that by 2, make it 24, right? And now we're 1. You can just do that for fun. Multiply the 1 into 24, though it won't change it. It's still 24. And then make n 0, and that's when we should stop, right? No more numbers to multiply in. Multiply all the numbers from 1 to 4. 0 is not included in 1 to 4. We kind of went backwards, and so we'll stop once we see 0. That'll be like our stopping condition. Okay? That's how I'm going to program this. I'll do it pretty quickly, though. That's not the main topic of today. Just the testing is the main topic. So this is going to be, I need a variable called, oh shoot, I have n. I don't think that's a problem, actually. We'll see. And then product. And then product. So, yeah, this is going to be weird. Set n to this n, the n that we get here. This will be the 4 or the 3. This is my variable n, though, my orange variable versus my red variable, which is funny. So again, when I call this, the 4 is going to get sent up and placed into this n, and I'm using the n down here. So set n to n, set product to 1, start them all off, initialize them, and then I'm going to loop. Loop until n is 0. That's when I stop. So repeat until n is equal to 0. The following. I want to repeatedly multiply n into product, so take product, replace it with itself times n. So set product equal to multiplying itself, whatever its current value is, by n, and that'll change it to some bigger value, in theory. And then I also want to decrement n each time, so I can multiply the next number n. So change n by -1, let's say. Okay. So that's the answer. And then I think that should do it. So this is going to set product to something, and then I guess we can print it out. Why not? Let's print out our answer. The answer is going to go in the product variable. So let's say product for 2 seconds. All right. And so then, say product for 2 seconds, sorry. So then when I run this block, it should compute and then say 12, right? That could be the test. Test. Make sure the answer is 12. That'll be one test. Or sorry, it should be 24, right? Excuse me. So that's my first test. So I run this, and it says 24. Cool, it worked. That's how you make a test. Make sure that the answer is 24. Any questions about that? So that's the code. There's a test. Multiply all the numbers from 1 to 4. Can I make this any smaller? It's kind of very large. There. That's one test, and we should make a bunch, right? Test the corner cases, right? So let's test, that's what you should be doing when you write code, right? Because maybe, like, 4, 1, and 2, those all make sense. Let's, like, try to multiply the numbers from 1 to 0. Multiply all the numbers from 1 to -1. So corner cases, that's a technical term, I guess. That's the cases where things are almost going to be a normal answer, and they're almost like error inputs. So almost correct or almost not correct, or where the program is about to do something different. So good corner cases here, because we're checking for something to be 0, maybe our good corner cases are like 1, 0, 2, -1, stuff like that. Those are good corner cases where we don't want to do anything at all, kind of. Okay, so let's see what those are. Duplicate. And I think you can imagine what should happen here. So multiply all the numbers from 1 to 1, that should be 1. Cool, that test passes. That really does do what we think it should do. Multiply all the numbers from 1 to 0. Should that be like an error, maybe? I don't know. It's going to give back 1. There are no numbers from 1 to 0. Is that a good enough answer? Maybe it shouldn't be. That's up to you. Multiply all the numbers from 1 to 2. That should be 2 as an answer. Okay, yeah, 2. That's correct. And then you want to test some very bad cases as well, like totally incorrect cases. What should the input do on -42? Maybe we should just yell at the user, like, you can't, I'm not going to work with a negative number. Let's try and run this. Look at how I have an infinite loop right now. So my code is actually incorrect. Thanks to this test, I noticed that there's a problem. If the user gives me a weird value like -42, my program's just never going to stop. See how like n is increasing larger and larger? So that's going to inform my code. I have to change my code now if I want it to be correct. That's no fun. So let's do it like this. Let's be like, let's have an if. I don't know. Let's do if else, maybe. If then else. So, oops, let's get that out of here. I'm going to have to move all these down a little bit. I don't want them to be connected, but that's Scratch doing that automatically. Go over here, go over here, go over here. There. If I stagger them, it should work. So let's make sure that the user didn't give me a bad number. Like, it probably doesn't make sense to enter 0. It definitely doesn't make sense to enter -42. So let's make sure that n is greater than 0. Because then I'll get always into a good case, a case that works. I won't infinitely subtract 1 from n and pray that it will be eventually 0. But it's already smaller. So let's make sure that we only do our stuff when n is greater than 0. If n is greater than 0, then I can actually do what I cared to do. Say product for 2 seconds. Otherwise, let's complain. Let's be like, this is what should happen in the error case. Just say, I don't know how to calculate this value. I can't multiply numbers from up to that number. Something like that. And so now, like all the other things should still work. 24, 1, 0 doesn't work anymore. -42 doesn't work anymore. I can't multiply up to that number. 2 still works. So maybe that's a better program. You see how thinking of all these tests, like almost correct cases, cases that are close to what they should be, like the last values that my program still makes sense for, and then totally incorrect cases. And then finally you have some normal cases like 4, 5, and 8. Let's just pretend that 4 was a good enough one. But you can keep on going. 5 is supposed to be 24 times 5, so that's apparently 120. Those are tests. You always compare what you got with what you expected. And if you make enough tests, and there are a bunch of different kinds, they test different things, then you can be pretty confident that your program is doing the right thing. Okay? Any questions about that? That's definitely a more advanced topic, but it should make some intuitive sense, I think. Am I good with that? All right, so I think that's where I want to stop today. I'll give you this code for fun. And yeah, no new assignments this week. That would be evil just after the exam.